on to topic 2, and we're going to be talking a lot today, or a lot in this particular recording, about stereoisomers. So that's all your configurational, conformers, diastereomers, all that fun we had last semester. So we're going to do that again in this lecture. So, as I said, all the terms that we're going to have to get used to and remember are up on the screen. So constitutional, conformational, configurational, enantiomers, and diastereomers. We're going to talk a little about the energy of conformers, particularly as you twist them in space, and you have had those conversations, I think, particularly with Greg, just before you changed over to me last semester. One of the main, we are also going to talk about E and Z isomers, but what I really want to cover, and this is new to you, is how to determine R and S nomenclature around enantiomers. So the last couple of slides, or one in particular near the end, is brand new. So most of this you will have covered before, but there is one new piece of information here. So firstly, let's start with this idea of why we're even talking about stereoisomers. And it comes down to a central point that whilst we can write down all the elements in the formula of a given molecule, as you can see this example on the screen, we have literally no idea how that's bonded. We have no idea how it's arranged or how it makes any given structure. So we have to accept that there is a whole bunch of ways that that could be bonded. There are many different examples that could match this formula, and we need a naming system that allows us to tell them apart and talk about them differently. And in particular, this is very important because some of them may not have different properties, some of them may be vastly different to one another in terms of reactivity, and a whole bunch of physical determination. Things like melting point and boiling point can change drastically depending on how that bonding is formed. So in this particular example, there's an insane number of options. There's 16 different ways that we could rearrange these elements to give legitimate compounds that could exist. All of the bonding structures for all of the elements are held. They're all holding to the valence rule. So we can see there's a lot of different options here. And there's some structures you've never seen before. These 3-membered rings with 2 carbons and an oxygen, known as epoxides, are a bit of a weird one for you guys because you haven't encountered that yet. And we are ignoring the idea that you can actually even get O-chlorine and O-bromine bonds. And so quite frankly, just knowing the formula isn't enough. We need to know a lot more about the structure in order to know what we are actually dealing with. So one way that we handle that is to name the isomers that we're dealing with and to start to understand what is the difference between different molecules. When I'm looking at one structure or another, are they completely different in terms of their arrangement of bonds? Do I have to break things? Are they just orientations of one another in space, just rotating around bonds? Are there mirror images involved? Are there double bonds? That's what all this language is here to help us with, so that we can talk about it more succinctly. So the first thing we're going to talk about is this idea of constitutional isomers. Now you have to remember that firstly, isomer means that whatever we're comparing, whatever we're talking about, they have the same molecular formula, same elements in that structure. If they're different, then it's a different molecule altogether. So firstly, isomer means same molecular formula. After that, we're dealing with constitutional. Now, constitutional isomers are those that are different to one another because you had to break a bond to turn one into the other. Now, early on in our alkanes, that's impossible. You can't actually break the bonds and rearrange them to form another unique compound, so they have no constitutional isomers. It's not until you get to butane where you can break off the terminal methyl group and move it inside the molecule itself. So those 2 different constitutional isomers would match the molecular formula for butane. Same number of carbons and hydrogens, but the bonding is different. And the only way for me to make them the same as one another would be to break a bond and move it elsewhere onto a different carbon elsewhere in that structure. And so that's what we mean by constitutional isomers. It's all about having to break bonds and move it across the molecule. This is very important in terms of exactly how this bonding is occurring, because we will change drastically the reactivity of the systems based on what that bonding looks like. So here we have 4 different examples. All of them have the same molecular formula, but they've all changed their reactivity because of how they are formed and how they currently exist. For example, we've got a ketone and an aldehyde. To certain conditions, aldehydes are far more reactive. We covered oxidation last semester. The aldehyde can further oxidize to a carboxylic acid. The ketone can't. So we're getting a very drastic difference in reactivity because they've got that different bonding structure. And then we can have things like an alkene ether or an alkene alcohol. Both of them have the alkene, but the ether is not particularly reactive to anything. They're very stable groups, whereas that alcohol could be deprotonated by a very strong base. So it starts to have a level of reactivity. We also know, of course, that alcohols can be combined with carboxylic acids to make an ester, whereas our ether, we can't do anything with it. So the bonding of these structures are very, very important in determining what they're going to do and how they're going to act. After constitutional, where we would have had to break a bond and move something elsewhere in the molecule, we're talking about stereoisomers in general, and these are different arrangements in space of the elements in the bonds around a central core. There's 2 different versions of that. There's conformational and then there's configurational, where if I rotated around a single bond and it was an allowed rotation, that's conformational, where if it was disallowed and I had to break a bond as I was rotating, that would be configurational. So let's talk through those a little bit more. So as I just said, conformational is rotation around that single bond, and they tend to rotate incredibly fast, hundreds of thousands of times a second. And part of what's challenging with conformers is because they're moving so quickly, we can't really isolate them from one another. If you have both conformers in solution, half a split second later, they could be the same, they could have rotated it slightly into a different arrangement, and so we can't really separate those relatively easily. Configurational, however, as I said, if we're trying to rotate around a bond in those cases, we'd have to break a bond to do it. So that's something like a double bond or a ring. So that requires a lot of energy. So it's much, much easier to separate configurational isomers because they do have slightly different reactivities. They can have slightly different melting or boiling points. And so we can pull those apart, unlike conformers, which that's generally not going to happen. So most of our rotation that we're interested in, the simplest one, is in a straight chained alkane. Around any given carbon-carbon bond, the entire system can rotate. That's much more easily seen in a model if you have the ability, or there's plenty of videos up on YouTube as well, watching these things rotate around the carbon-carbon bond. For a cyclic alkane, however, if I was to try and rotate the structure around that carbon-carbon bond, I'd have to break the ring to do so. So it is a restricted system. So rotating around the straight chain alkane will result in conformers, but for these structures, it can't be conformers. We can't rotate around that bond, and so these are configurational isomers. We'll talk more about that as we go further in. There's a couple of different ways that we can represent these conformational isomers when we're talking and comparing them. We can go for what is called the seahorse representation, which is allowing us to see the entire structure on an angle all at the same time. And we can consider where this rotation has occurred by where we've drawn the hydrogens on the page. So in the top left one, those 2 hydrogens are pointing bang along on the ring that we're interested in. And then going to the top right, we start to turn one of those. Actually, it might be a bit better if I turn this one for you. So we're turning this back carbon and moving that actual bond along. And we can, whenever we want to flatten that out, we can look down what is called the Newman projection. So you see this little eye on the page, and we're looking down the carbon-carbon bond, and we're acting like we've flattened the entire structure in order to see what's happening. When we started on the left, I told you that the 2 hydrogens were aligned with one another. So on a Newman projection, we would show that by putting them right next to each other. When we've rotated by 60 degrees, we've moved one of those out on an angle. And again, you can see that red hydrogen has moved onto a slight angle with the green hydrogen, but now it's in the back. The terminology that we use for this is when those hydrogens overlap, or whenever those substituents overlap, we call that eclipsed. And they will, once they get larger and larger, actually clash into each other in space. They'll run into the same physical environment. And so an eclipsed structure is a little less stable. For staggered, they move out of each other's way, so there's no what we call a steric interaction. There's no physical clash there. So the staggered is a little bit more stable in this particular case. And they're really, really useful for looking at these structures and considering the stereochemistry of them. So as I was just discussing a moment ago, we can map out this rotation showing the higher energy eclipsed states at the higher energy position, and as it rotates and moves throughout that bond, it gets down to the much lower staggered state. Note that that's only about 12 kilojoules per mole. It's actually relatively low. There's enough energy around at room temperature, to allow that rotation to continually happen over time. And this is particularly well noted when you compare the energy of rotation, 12 kilojoules per mole, to the bond strength, which is about 350 kilojoules per mole. So it's a vast difference between the two. And this is all due to what we call these steric interactions, these physical clashes in space between the different substituents. So up until now, all the rotations that we've been talking about are around an allowed bond. I did refer earlier to the idea of double bonds and rings disallowing that, however. So the examples you can see on the page here are, of course, all those double bonds. And if we were to look at this bottom example here with the 2 carboxylic acid substituents, we can't relatively easily rotate around that central double bond. To do so would require us to break the double bond, which requires a lot of energy, so it doesn't tend to happen. So we can actually isolate these systems from one another, and they are different, and they're referred to as configurational or geometric isomers. This terminology, ZE, cis-trans, I'll explain now. And ZE are really, well, they're German for Zusammen and Entgegen, which is a fun word to try and say a lot or many times quickly. Importantly, what you need to remember is that Z and cis mean that your substituents are on the same side of the double bond, whereas E or trans means they are on opposite sides of that double bond. When we're referring to the substituents themselves, we're talking about the atomic number of the first atom attached, not the entire thing. So you may have a huge, massive molecule on one side, but if it's got a carbon attached to that double bond, where the other substituent had an oxygen, the oxygen would win. It's the atomic number, or more accurately, the molecular mass of the exact atom bound to that carbon. So don't look for the whole structure, look for the one atom that is bound. That's what's going to tell you whether or not we're looking at Z or if we're looking at E. Just to be a little bit confusing, I mentioned a moment ago that these are called geometric isomers or configurational. They do annoyingly have a third name, which is a diastereomer isomer, or often collapsed down to a diastereomer. So all those terms are referring to the same thing here. And we'll come back to diastereomer because we're going to have to talk about it again around chirality. So let's have a look at some examples to help us understand this a little bit better. So on the left-hand example, we have the 2-butene. And if I'm looking at the direct elements attached, carbon is a higher molecular mass than hydrogen. So it's going to be the substituent that takes priority. So the 2 methyl groups do. And at the moment, they're on the same side of that double bond. So that gets a Z2-butene. In the next example along, they're now on opposite sides of that double bond. So we're looking at E2-butene. Remember, of course, that that could have been cis-2-butene and trans-2-butene respectively, because Z and cis, E and trans are talking about the same thing. Last example here, where we have 3 different substituents on this same alkene, we do need to think about the individual elements attached. So we've got hydrogen, bromine, chlorine, and carbon. Bromine is definitely heavier than hydrogen, so it's going to win out on the left-hand side, and chlorine is heavier than carbon. so it wins out as well. So our bromine and our chlorine are the substituents that take the highest priority. They are currently on opposite sides of the molecule, so that is E in that particular case. So that's hopefully helped you out a little bit with how to assign E and Z to double bonds. This change in double bond structure is very, very important biologically. So these are actual isomers that exist in our eyes, and as light hits them, that does provide enough energy for them to rotate around that double bond. So it actually breaks open the double bond and reforms again. And because of that change in structure from E to Z, our eye actually detects that. That's what a part of how we see. These isomers change structure, we detect that, we get an electrical signal about that change, and we use that to know that light has hit the back of the retina at that particular time. It's quite complex, there's a lot of enzymes of course involved in that, but you can see all these double bond structures changing from more branched and collapsed to far more linear and taking up a lot more space, constantly going between those two structures as through this chemistry. So it's very, very important in this particular case for our ability to see. After double bonds, I did refer to this earlier, when we're dealing with cyclostructures, there's a couple of different ways that we can have isomerization. We can of course have constitutional, where we have to break bonds and move it around the structure. But if we're ever looking at, well, these would have been the same if I could have rotated about this bond, of course we're looking at configurational, geometric, diastereomer, all the same term. So just because there's no double bond here doesn't mean we can't have that same restriction. Double bonds and rings both result in these kind of isomers. We can also still look at the terms cis and trans. That works here just as well. So when our two substituents, our chlorines, are on the same side of the ring, it's cis. When they're on opposite sides of the ring, it's trans. So there's nothing to stop us using the same terminology that we use for double bonds on these rings. Importantly, just like the different double bond systems, they do have different physical and chemical properties, so we can isolate them, we can react them differently. They are quite different from one another. Last but not least, we're going to deal with the concept of mirror images. And we dealt with this before, but we're going to add a little twist in terms of talking about what R and S mean and how to assign which enantiomer that I am looking at. So we hopefully recall that we only ever have chirality when I have a central carbon that has 4 different substituents bound around it. The reason for that is when you have 4 different substituents around a central carbon and you take its mirror image, they can no longer be put on top of one another. So dealing with my hand, ignoring the band-aid, got my, there we go, left hand and my right. They are direct mirror images, but there's no way for me to put them on top of one another so that they are exactly the same anymore. So my hands are chiral. I cannot superimpose them on top of one another when I've taken the mirror image. Note that within the molecule, so within my hand, for example, there's no internal plane of symmetry. I don't have 2 thumbs on either side of my hand. So that's a part of what helps us determine, yeah, it is definitely chiral. When I have more than one substituent that is the same around that central carbon, its mirror image is just a rotation of itself. So it's usually a conformer in this particular case, so it wouldn't be considered chiral. So we're finally at the point now of talking about R and S and how to determine which enantiomer you are looking at any given point in time. We do that through the priority system in the same way that we determine priority for the double bonds. So that is the molecular mass of the element directly attached. If we look firstly at this example on the left, we had 4 substituents bound around that carbon, and the closest ones are chlorine, hydrogen, bromine, and another carbon. Of those 4, hydrogen is the lowest priority. So we rearrange the molecule so that is pointing away from us with the wedge bonds. After that, we only need to pay attention to the 3 substituents left on the board. So here we have bromine, chlorine, and carbon. The highest molecular mass is bromine, so it gets number 1. Chlorine is next, number 2, and carbon is last, number 3. We then draw a circle. either going one direction or the other one. So if we go from bromine to chlorine to carbon, I've drawn an anti-clockwise ring. Because it's anti-clockwise, we refer to that as S. That's just the nomenclature and the convention for how we name these things. If I'd drawn that the other way, going clockwise, I'd refer to it as R. A good example of it, again, is on the right-hand side with ibuprofen, which is commonly found in Nurofen as a pain reliever. If I look at these three substituents around that chiral carbon, actually the first element out is carbon 3 times around, so you can't tell the difference between them. So to determine which one wins, we go one element further out, so always one at a time. So for the carboxylic acid, the next elements out are oxygens. For the aromatic core, the next elements out are carbons, and for the methyl group, the next element out is all hydrogens. So the heaviest of those were the oxygens, so it gets priority 1. Then the carbons, so the aromatic core gets priority 2, and then finally the methyl group at the top gets priority 3. If I drew a circle between those from 1 to 2 to 3, clockwise and R. For the example on the right, it's going to switch around, so the same priorities, but they're elsewhere in the molecule because we're dealing with its mirror image. And here what we'd find is that if I drew the circle from 1 to 2 to 3, I'm now anti-clockwise. So that is S. What's interesting is how much this matters. The R enantiomer doesn't do anything. It doesn't help us with pain relief. We can take it, it passes through, it's irrelevant to us. The S enantiomer, however, has significant pain relief properties for human beings. So what enantiomer we're looking at is vitally important, and we need to be able to determine them and name them. You can watch this YouTube video below to get some more help around it. Hopefully this has started to make sense to you. Alright, and with that we can wrap up this second topic. So obviously we've gone through all these terms again: constitutional, conformational, enantiomers, configurational, and diastereomer. I didn't touch as much on diastereomer, so just very quickly, remembering that diastereomer also referred to double bonds, the disallowed rotation around rings. It also counts for when you have multiple chiral centers, but only one of them has been inverted through a mirror image. It's quite a catch-all term. There's a lot of things that actually count as a diastereomer, but importantly, they are not mirror images of one another. That's a big part of the definition of a diastereomer. We talked about the energy considerations of a conformer, that it was very, very small actually, and that those rotations could rapidly occur at room temperature, and that the energy required was much, much less than that required to break a bond. We know how to determine the difference between E and Z, looking at the highest priority of the nearest attached atom to the alkene. If they're on the same side, Z. If they're opposite, E. And last but not least, we also talked about how to know the difference between R and S, using that same high priority system, but determining whether or not it goes clockwise or anti-clockwise. With that, have a go at the worksheet that covers all the stuff that we've just been talking about, and you can go to that video to see if it's made sense and you can follow my answers to it. Best of luck, and that's the end of this particular topic.